Do 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 do. Okay, so building on solution stoichiometry and mixed stoichiometry is something called titration. And titration is a good application of solution stoichiometry. Basically, and as it says here, titration is an experimental process to determine the unknown concentration of a solution by reacting it with a different solution of known concentration. So I have two solutions. One is usually an acid, one is a base, and I know the concentration of one of them. I can find the concentration of the other one using this method called titration. We have to do one other thing here, and it says in the second part of this wording is an indicator is used to show a color change when the reaction has reached completion. So a titration is all about changing colors. Our solution is going to change colors when we've reached the completion, or what's called the end point. And when we've reached that end point, we're going to know a number of things. We're going to know a volume of both solutions, and we're going to know the concentration of one solution. Hopefully you can see where we're going. If you know the concentration and volume of one solution and the volume of the other one, you can find the concentration using solution stoichiometry. So titration is just solution stoichiometry with one additional step at the start. So here's the setup, and then I'll show you how we'll actually do a calculation using this. So we have a stand right here. On the stand, it has a post with a clamp on it. That clamp is holding what's called a burette. And one of the solutions, the solution that we know the concentration of, is going to go into our burette. The burette has all these different volume markings on it, and what we're going to do is we're going to be able to measure out a volume of this solution that we used. The solution inside is called the titrant. We have a lever or a tap right here and a flask down below that we are going to drop the titrant into. In this flask is going to contain our solution that we don't know the concentration of, our analyte in this case. So here's an actual picture from over in the lab. So here is the experiment I did this morning. Here's my stand with my clamp. The burette here, you can see it has markings all on there with the tap down here. I don't have a flask underneath, but you can see some in the background here. And on the actual burette, you can see the different markings. So each of these 2, 3, 4, 5, 6, those are milliliter markings. There are 10 in between, so those are 1/10 of a milliliter. And if you remember from grade 10, when we measure something, we actually estimate one more digit after that. So you would get down at eye level. This picture is not super good. It's not right exactly on eye level, so we'd have to eyeball it, but you can see this one would be 3.5, so 3.6, 3.7. We're just a little bit, it would appear, below 3.8. So I think when I recorded it, I put down this was 3.78. And then through the process of titration, this volume is going to drop. Let's say we end up exactly at 7. Well, the volume of titrant that we used would just be the difference between those two. So here's an example. You'll see in my other video how a titration experiment actually works. So let's take a look at this example though and do some calculation before we actually go ahead and do the experiment. So we have several 10 milliliter samples of acetic acid are titrated with a 0.50 molar solution of sodium hydroxide. What is the concentration of the acetic acid? Now I've given you the reaction here. Really I should probably have in that these would all be aqueous, so we should have their states as well. Remember, any acid is going to be aqueous. Any, for this base, sodium hydroxide, you have to look that up, but this would be aqueous as well. This product's aqueous, and HOH, remember, is water, so that would be liquid. Okay, so what do we know here? Let's switch to blue. So we're given 10 milliliter samples of acetic acid. So there we go there. And finally, we're asked what is the concentration. So I don't know my concentration. I do know a concentration of sodium hydroxide. So that's the concentration here of 0.50 molar. Okay, this is beginning to look an awful lot like a solution stoichiometry question. This acetic acid is our wanted, or our unknown. The sodium hydroxide, even though I just know the concentration, I will know the volumes here as well. So this is going to be my given. So we've identified given and wanted. What would we do? We'd figure out moles of this, use a mole ratio to figure out moles of this, and then we can convert to a concentration. So now I told you I actually know the volume of sodium hydroxide. If we do this experiment, we're going to get experimental values for volume. We do more than one trial, so we repeat the experiment a number of times. And the reason for that is because we're humans and we make mistakes. So the more trials we do, we can find an average volume, and we can hopefully have a volume that would be pretty accurate by taking the average. So my volume here is going to be the average of trials. And I'm going to put one more thing here. Our trials have to be within 0.2 milliliters of each other. So when we actually do this experiment in the lab, some people will take 5, 6, 7 trials to get 3 that are within 0.2 milliliters of each other. And that's what we're looking for. We want 3 trials that are within this. Some people, the first 3 trials that they do are all in very close agreement, and they just take the average of that, which is awesome. Sometimes it takes longer. So this is the data table that you would fill in here. So we've got trial 1, we've got an initial burette reading, a final burette, and the total volume is just the difference. So I'm going to just give you some numbers here. So let's say we start off at 40.75 and we end up at 22.23. Well, that's a difference of 18.52 milliliters. Trial number 2 goes ahead. We start off with 22.23 and we end up with 3.40 for a difference of 18.83. Those are actually 0.31 off from each other, so one of those at least isn't going to be able to be used. We'd have to keep going. Trial 3, so again, I'm just making up this data here. We get a difference of 18.60 milliliters. So first and third seem to be in close agreement. Let's hope that the next one I give you actually works. Spoiler alert, it does. It's 18.53. So trial number 1, 3, and 4 all are within 0.2 milliliters of each other. So our volume of sodium hydroxide used would be the average of those 3. We are going to ignore this one. We will ignore in our volume calculation. So our average volume up here, let's say, let's do it down below. So extend our page here. So our average volume would be 18.52 plus 18.60 plus 18.53, all divided by 3. And that gives me an average volume of 18.55 milliliters. So now using that, take a look up here. We know a concentration and now a volume of sodium hydroxide. We can find the number of moles of sodium hydroxide, mole ratio to convert to moles of acetic acid, and then determine the concentration of acetic acid. So that's just a solution stoich question. So why don't we see it done one more time? So sodium hydroxide. So we know that C equals N over V. If we rearrange, that gives us N equals C times V. Our concentration was 0.50 molar, and our volume was this 18.55 milliliters. Remember, volumes need to be given in liters, so we're going to divide this by 1,000 to give us 0.01855. And when we do that, we get 0.009275 moles. The mole ratio here, I believe it was just 1 to 1, which is nice and easy. So X moles of acetic acid, which was CH3COOH, divided by 0.009275 moles of sodium hydroxide is a 1 to 1 mole ratio, so that's nice and easy. We don't really have to do any calculations. X is still going to be 0.009275 moles. And then for our acetic acid, we'll do concentration equals N over V. So we just calculated our N was 0.009275. And our volume, it said each of them were 10 milliliter samples, so that's 0.01000. Let's keep significant digits here. So that gives me a final answer of 0.9, and I'm going to round to, how many significant digits should we round to? We were given a concentration of 0.50, so that's 2 significant digits. So my answer should have 2 significant digits, so I'll have 0.93 molar, or moles per liter. So this bottom part is all just a solution stoichiometric question. The new part with the titration is you have to calculate these volumes used and then find the average volume of the trials that are in close agreement with each other. This one we did not use in our calculation for volume because it was too far removed from the other ones. It was too far away. The average volume is the ones that are close to each other, and then that volume is used in our solution stoichiometric calculations afterwards.